Okay, welcome back. This video that I'm creating today, its purpose is to teach you how to find relative extrema in functions that do not have a closed interval. So this is the beginning of objective 4.2. I encourage you to take a moment to pause the video and maybe take some of these notes. And as you do that, I'm going to go ahead and add a drawing for you. Okay, so the first thing is we've already talked about increasing, decreasing behavior. These statements here are just the official way of saying that if f increases as you move along the x-axis to the right, each point to the right will be bigger than the one on the left. But if the function is decreasing, then each point to the right will be smaller than the previous one. So it's basically saying as you move along the x-axis, if the function's getting bigger, you're increasing. If it's getting smaller, it decreases. It's just a basic definition of increasing, decreasing. Here's where derivatives are going to come into play. It says let f be continuous on a to b and differentiable on a to b. If f prime of x or f prime is greater than 0, meaning positive, what that's going to imply, and if you look at this picture, derivative, remember, is the slope of the tangent line. So if you look at the slope of the tangent line along this interval here all the way up to a, you're going to notice that it's a positive slope. So clearly this function is increasing, which implies that you have a positive slope. Now as you're decreasing, you get negative slope and then back increasing positive. So what is that going to mean for us? It's going to mean that whenever your function, your derivative is positive, you can automatically assume that f is increasing on the interval a to b. Notice the interval is closed. So increasing is defined as a closed interval, so you always have to use brackets. In the same frame of mind, if the derivative is negative, then f prime will be decreasing. Now, if f prime is 0 for all x in ab, what that would mean is that the derivative is always 0, so we're talking about a horizontal line. So f of x would equal some constant c. So that's the definition of increasing and decreasing officially. These are things, are notions that we've kind of worked for a while now. That increasing means positive derivative, decreasing means negative, and so we've just kind of been talking about it. Here's an example problem that you might see on a test or quiz. Find the intervals where f of x is increasing or decreasing and state your answers in interval notation. Well, the first thing you need to know is that when functions change from increasing to decreasing, it happens at critical points. The function that I showed you earlier behaves really nice. If you notice, it changes from increasing to decreasing at kind of a turning point, but that happens when the derivative here is 0. And if you recall, the derivative being 0 means we have a critical point. So here we have another critical point. So what we're going to do is that we're going to need to find the critical points first. So we're going to take the derivative. This is a pretty easy function to work with. 9x squared minus 16x. And we're going to go ahead and set that equal to 0 to find the critical points. And I'm going to just have you go ahead and work that out. I'm going to press pause and come back in a moment. Okay, so I went ahead and solved the equation. Hopefully you arrived at the same conclusion. These are your critical points. Once we've established the critical points, the next thing we need to do is figure out where the function is increasing, decreasing. And we're going to use this notion up here of positive derivative and negative derivative to help us with that. We're going to make a chart, a sign chart. And here we go. I'm gonna put, it's basically a number line here. And I'm going to add some points. I'm going to add my critical points. I'm going to put 0. And I'm going to put 16 over 9, which is not quite 2, but bigger than 1. And what I'm going to do is that I'm going to put f prime on top and f of x on bottom. And once you set the CPs, you know that the derivative at these CPs is 0 or undefined. For our particular example, it was 0. So we're going to put 0 here. My derivative was 0. Now, you're not guaranteed that you have a turning point at a critical point. It may not be an extreme, it may not be a turning point. So you first have to check by taking points that are surrounding these critical points and plugging them into the first derivative, not the original, into the first derivative. Now the answer doesn't really matter. What matters is the sign of the answer. If we get a positive sign for the derivative, we know the function must be increasing. If we get a negative sign, we know the function must be decreasing. So I'm going to go, you guys can go ahead and pause and compute those. I'm going to do that as well. The points that I chose were the easiest I could think of. To the left of 0, I chose -1. Between 0 and 16/9, I chose 1. And after 16/9, I chose 2. So those are points that surround, and I'm going to plug them into the derivative. Now, because I don't really care about the answer, I just really want to know the sign. You can kind of shortcut this a little bit. You don't actually have to evaluate the whole thing, although you can if you want to. But really, all I'm going to do is take my derivative, and I'm just going to think, all right, -1 times 9 times -1 minus 16. So this is going to be -1 times, this is going to be -9 minus 16. I know that that's going to be a negative as well because I'm adding two negatives. So a negative and a negative, the result is going to be positive. And I'm kind of shortcutting a little bit. Again, I don't really need to know the exact answer. I just want to know that it is negative. So for our purposes, this means that the original is decreasing, and I use my arrow to remind me of that. All right, now 1. If I put in a 1, I'm going to get 1, and then inside I'm going to get 9 minus 16. Guess what? That is still negative. So positive times a negative is going, negative times positive is, I don't know why I'm having issues with that. That's a negative, so that's going to be negative here. And you know what? Let me go back a moment. I don't know why I put negative in the previous one. I had negative times a negative is a positive, which is positive. So that means that this derivative is positive. That was a mistake. Let me erase this guy. And what that would mean now is instead of decreasing, that's increasing. Yeah, that's why it was causing me issues. I was noticing I made a mistake there. So the result of f prime of -1 is positive, means increasing. The result of f prime of 1 is negative, so here we are decreasing. Which means, it's negative, which means the function is decreasing. At 2, if I put in a 2 to the derivative, remember all this is derivative work. I'm going to have 2 times 9 times 2 is 18 minus 16. Clearly that's a positive and a positive, so the result is positive. What that means then is I'm going to be increasing. So the question was to state my intervals of increasing or decreasing. I'm ready to do that now. For this particular example, the function will be increasing, and if you remember, increasing is defined in closed intervals. Now, we can't really close negative infinity, so that one has to have an open bracket or an open parenthesis, but it does go to 0, and I include 0. And, oops, I forgot one more. We're also going to be at 16/9, and we're going to go all the way to infinity on that one. And decreasing then would leave us with 0 to 16/9. And that's our answer. Now, these should be brackets as well. Most students will then ask themselves, why do you have a bracket on 0 for increasing, and then now you have a bracket for 0 decreasing? Is 0 both increasing and decreasing, and how is that possible? Well, it depends on how you look at it. If you think of 0 as part of this particular interval, negative infinity to 0, then it's increasing because the y value at 0 is going to be higher than the previous y value. But if you think of 0 as part of this interval from 0 to 16/9, then 0 is going to be decreasing because it's going to be the next value after 0 is going to be less than 0 itself, the y value for that corresponding point. So basically it's because it depends on which interval you're in, okay? And the same thing goes for 16/9. I'll clarify that tomorrow in class more. So that's how you do increasing, decreasing. Set the derivative equal to 0, or undefined, find the CPs, make a sign chart, and test points surrounding those CPs. Make sure you test them in the derivative, not the original. So the first derivative test, let's talk about that. That's the next thing in line. Well, I have a nice image here, and I gave this to you to put in your notes, but here's what I want you to notice. If you have a local max right here, the derivative before that local max is going to be positive. Use a color you can see. But after that local max, the derivative is going to be a negative, meaning that if you have a max, before, your function should be going up and after down. So you should have a positive to negative change in derivative. Look at this one. This one happens when the derivative is undefined. But still, before that, you have a positive derivative. And after that, you have a negative derivative. So again, you get a sign change that is positive to negative. So what does that mean for us? It means that f of c, a y value, is a relative max if the derivative changes from being positive to negative. Okay? Now, if you go to a relative min, what you're going to notice is that the derivative goes from being negative, because the function is decreasing, to being positive. Okay? So the sign change, a sign change in the derivative happens again, but this time it has to be negative to positive, because the function must have been going down and then up in order to create that min. Last thing, you see here we have a critical point that the derivative does equal 0, but we discussed before that that's not an actual extrema, because it is neither higher nor lower than both sides of the points that are around it. So what that means is that if you look at the derivative before this extrema, it's before this critical point, it's positive 0, and then after it continues to be positive. So there was no sign change. If there's no sign change in the derivative, then f of x, or f of c, sorry, in this case is neither a max nor a min. So this happens if f prime does not change signs. Put that in there. Change. I'm having some, my technology is signs. Okay? Because there was no direction change. So that's kind of what I wanted to set the stage for the first derivative test. The first derivative test is a way of testing to see if critical points are maxes or min. And this is really it. This is the first derivative test is really, this is what it is knowing these three things. Sometimes it's hard for students to memorize, but I always kind of tell them don't memorize, just, kind of draw a max and you can see it goes positive to negative. Draw a min and you can see it goes negative to positive. Now you can also have, a critical point that's undefined. So when we look for critical points, we got to consider zero derivative and undefined. So let's work an example here to see how this works. I'm going to work one that's easy, and then I'm going to work one that's a little tougher. The first one is just a regular polynomial. We're going to find the intervals where it's increasing, decreasing, and relative extrema. What you're going to find is that this is really exactly the same process that I just did in the other flip chart, in the other page about increasing, decreasing. The first thing you need to do is find your critical points. So I'm going to go ahead and put g prime of x equal to 4x cubed minus 4x. And I'm going to set that equal to 0 because I'm finding my CPs. It's not going to be undefined, so just CPs from derivative 0. So 4x gives us x squared minus 1. And that's still equal to 0, which means x is equal to 0, or x squared is equal to 1 from setting this one to 0. So this is going to give me two answers for a total of 3, plus or minus 1. When you take the square root of both sides, that happens. Okay, so these are my CPs right here. Okay, so what I'm going to do now is I'm going to go ahead and make a chart, sign chart, and I'm going to put my derivative on top. Sorry about that, let me click on the pen. Put my derivative on top. And then the function behavior on the bottom. CP's are graph first. I'll go with -1. Then I'll go with 0 and then 1. We already know that the derivative is 0 at all of these. So you can write that down. You have a 0 derivative here. So we just need to test points around it. Again, we're going to plug these into the derivative and we're going to check the sign, not necessarily the answer. Okay, so I don't care if it's -6 or -3. I just know that it's negative and that's what matters. Okay, so we're going to take a point, let's say negative before, like -2. And I like to use the factored form because it's easier to plug stuff in than the original, derivative. But both of these work. It doesn't matter which one you pick. I like the factored one because I can say, all right, if I have a -2, I'm going to have 4 times -2 times -2 squared is 4 minus 1. So clearly this out here is going to be a negative. For -8, this is going to be a +3. When you multiply a negative times a positive, that is a negative. So that's decreasing. Now I'm going to use something between -1 and 0, so a -1/2. So let's see, that'll be 4 times -1/2 times -1/2 squared is a 4th squared minus 1. So this is clearly going to be negative, also negative. So that gives me a positive. All right. Now I'm going to use a +1/2. So in that case, I'm going to get a, let's see, it's going to be 4 times +1/2 will give me 2. So that's positive. Times 1/4 minus 1. So I have a positive and a negative. So that's a negative. Then I go down. Then let's say 2. Let's use +2. So we have 4 times 2, and that's going to be 4 minus 1. So clearly all of this is going to work out to be positive. So I get my sign chart done. You can tell the intervals where it's increasing and decreasing. You would write those, remember, with brackets. So this would be -infinity to -1 with bracket for decreasing, and -1 to 1 bracket. But I'm not going to write those down. I'll spare you that. But I do want to talk about this. If you kind of follow this curve, you can see that it's almost like sketching it. It was going down. Now I don't know how far down, but I do know that at that point it turns around to go back up, and then back down, and then back up. This is an exact sketch of what it really looks like, but I know these are turning points because of the sign of the derivative. So that allows me to tell right here I've got a local min. I've got another one over here. Now I don't know if it's absolute. I don't know which one's lower. For that I would have to compare the y values. But for sure I got a local min at x equals -1 and 1, and a local max at x equals 0. Now sometimes, and especially in your assignment, I'm going to ask you to put the coordinates for these. If you want the coordinates, then you got to take these points and you got to send them back to the original function and plug them in to get the actual y value. Again, this is where the local max is located, local min is located. But if you want to actually know what the local max, local min, y values are, you need to go back to the original and plug them in. So what were the steps? Set the derivative equal to 0 or undefined. Locate your CPs. Make a sign chart by putting your CPs on it first, plugging numbers that are around the CP into the derivative, checking for a sign, and whenever there's a sign change, you're going to have an extrema. But if it changes from negative to positive, it's a min. If it changes from positive to negative, it's a max. Keep in mind, if it does not change signs, then it's nothing. Okay? All right, I'm going to set up the last one, which I think is a little bit tougher, and then we'll continue. Okay, this last example is going to be tough because it's a rational function and you got to do the derivative. I'm going to just ask you to stop and take the derivative using the quotient rule, and I'm going to do the same and then show it to you in the end, okay? And then we'll continue. Okay, so here's my derivative using quotient rule. I'm going to go ahead and set it equal to 0, and I can get an answer. It's going to be x equals 0, the numerator, if you multiply everything by the denominator. you get x equals 0. Now, if I try to check for and define x squared plus 1, anything I square is going to be positive, and anything positive plus 1 stays positive. So there's no way I can get 0. So really, this was kind of seemed more complicated, but it only gave me 1 CP. And that's okay. So I'll just come to my sign chart, put my 0. And I already know that the derivative there is 0. And don't forget, you got to label this f prime f. In the future, we're going to make a sign chart with the second derivative, and it's going to mean something different. So it's important that you label. Students always fight that, but just do it. It will help us in the future. Pick a point less than 0, maybe -1, and I put that into the derivative. Again, I'm just concerned with the sign. So I'm going to get -4 times -1. On the bottom, -1 squared plus 1 is 2, and that's going to be 4 if you square it. So clearly this is going to be a positive result. So positive on the top means increasing for the function. If we put in, and you always got to check the other side. You can't assume that it's going to turn negative. It might stay positive. If it stays positive, you have no extrema. So let's put in +1. So that'll be -4 times 1 over, again, 1 plus 1 is 2, squared is 4. So this one came out negative. So that means that it is decreasing. So if we wanted to give intervals of increasing, decreasing, of course, -infinity to 0 included. For increasing, 0 to infinity. For decreasing, and this is our relative max. Now, we're testing only for relative max, but if you look at this function goes up and then comes down, and it never really goes back up. So not only, sometimes the charts will reveal that not only is this a local max, but it's also a absolute max. So it's an absolute and relative max. Sorry, my pen's giving up here at the end. So yeah, it's not going to let me write it. It's not going to let me write it, but you can tell that that's both an absolute and a local. Now, if you were interested in finding the actual coordinates, then you'd have to go plug that 0 back into the function, okay? And of course, you would get 0. And just so you see what that would look like, I have it on Desmos. Let me take this guy off. And this is what it looks like. So you can see it's an absolute max. And the absolute max happens at 0, and it happens to be 2. Okay? Alright, so that's the first derivative test. I'm going to post this video. Hope it helped. And you guys can practice the assignment I put on Canvas. See you tomorrow.